This problem is an application of measurement and uncertainty. A list of variables are provided and is asking to use these variables to calculate the resistivity of a wire with its value and uncertainty. So let me show you how to do this. This table provides the measurements for a sample of metal wire for length, diameter, and resistance. The measurement for the length with its uncertainty, diameter, and resistance. This first question is related to the appropriate instruments used to measure length, diameter, and resistance. This is a metal wire, and I can use a ruler to measure its length. So meter rule, not a ruler. For the diameter, because this is kind of a circular, cross-sectional area here is circular, I can use a caliper. So in this case, it's showing that the diameter is 15.3 millimeter. And for the resistance, I can use a multimeter on the ohm setting. The next question is asking to show that the resistivity of the metal is calculated to be 4.86 times 10 to the minus 7 ohms meter. So this is the value. We do not have to be worried about uncertainties at this point. So we have the formula for resistance in terms of resistivity, the length of a wire, and the cross-sectional area of the wire. Why am I using this formula? Well, because here on this table, that's what is provided. So that gives me a clue that this is the formula that I should be using to calculate resistivity. So rearranging the formula in terms of resistivity, so we have the resistance times the area over length. So now we are going to make all the substitution, but there is a situation here. We don't have the direct value of area. We need to calculate the area first, and then we have the value of resistance, and we have the value of length. Now notice, because the unit is meter, and all this is provided in millimeter, we need to convert all these variables here to meter. Since the wire has a cylindrical shape and the cross-sectional area is a circle, the area of a circle is pi over 4 diameter square. So the diameter was given, which is 0.38 millimeter. Now remember that milli is 10 to the minus 3. So we just need to add here, replace the prefix milli to the power of 10 exponent, which is 10 to the minus 3. So this way we can make our substitution here and calculate the area. Another way to do this is using the formula. Area is pi r squared. Now, because the diameter is this value, so the radius will be the diameter divided by 2, and we can just divide 0.38 by 2 and have 0.19 times 10 to the minus 3, all this is square. Then the next step is to make our substitution. We have the value of the resistance, which is 7.5. The area, I'm using the area of using the radius, which is this one here, which will not matter. Each one use this one or this one. I'm just using this one. Pi times 0.19 times 10 to the minus 3, all this is square. The length is this value. Now what I'm doing here is the m for milli, I'm replacing with 10 to the minus 3 to make it easier to write down. So after plug all these values in the calculator, so that's what I have. Now I need to write this in scientific notation. So I'm going to use a 4.86, so I'm going to move the decimal to the left. So it will be 1, 2, 3, 4, 5, 6, 7. So the value of my resistivity is 4.86 times 10 to the minus 7 ohms meter with 3 significant figures. Our next step is to calculate the uncertainty of the resistivity. So we need to look here the formula. The resistivity is in function of the resistance, the cross-sectional area, and the length. So we need to find the fractional uncertainty of every single component of this formula. So let's start with the fractional uncertainty of length. So we represent by the fractional uncertainty with this format, and the numerator is the uncertainty and the denominator is the value of the length. So that is the fractional uncertainty of the length. Next, the fractional uncertainty for the resistance is the uncertainty over the value of the resistance. Now notice that in both cases, the units are canceled. The units for both the value and the uncertainty, which means that the fractional uncertainty, there is no units here. Now I left the last fractional uncertainty, which is the uncertainty of the diameter, for the last to explain in this problem, because if you look, the diameter is not directly in the formula for resistivity. So why am I calculating the fractional uncertainty for the diameter? Why not the area? Well, because when you look at the area here, we calculate the area in terms of the diameter. If we say, well, why not in terms of the radius? The radius is still in terms of the diameter. So diameter here is the base measurement to find the area of this wire. So I have to look at the uncertainty that the measurement of the diameter is adding to the final measurement. So that's why I'm using the diameter. Okay, so now we have all fractional uncertainties of the components of the formula for resistivity. Now we need to combine them. To find the fractional uncertainty of the resistivity, we need to add all the fractional uncertainties of the variables that make the formula for resistivity, which is R, A, and L. One more time, that A is not directly showing here. Instead of is the diameter is the one that will be adding uncertainty to this area. So that's the only measurement that we did for this problem is that is showing here was the diameter. So we are calculating just the fractional uncertainty for the diameter. Now what I'm going to show you here is very, very important. The diameter is square. So it's going to add uncertainty twice. So for that reason, we add 2 times the fractional uncertainty of the diameter. If it was cube, then you'll be 3 times. So you do 3 times the fractional uncertainty of the diameter. So adding those values, 0.026 plus 0.0017 plus 2 times 0.026. So I get 0.0797. Next step is to add a unit for this fractional uncertainty because they do not have units, right? So we have a value for our resistivity, which is this value. So what we are going to do here is our uncertainty will be the rho times 0.0797. So to find the uncertainty of the resistivity, so I get this number here times 4.86 PE negative 7, and I have this value right here. To have a consistency with the power of 10, because that's the value of resistivity, so my uncertainty for the resistivity will be, you have the same format. Rounding the value of the uncertainty for the resistivity, we can 0.39, we can round to 0.4. Likewise, we can also round 4.96 to 4.9. So the final answer for this question is the resistivity with its uncertainty with the appropriate number of significant figures. Here we have 2, here we have 2. So is 4.9 times to the minus 7, 0.4 times 10 to the minus 7 ohms meter. So make sure that you review all the steps to calculate the value and the fractional uncertainties of all the components for the resistivity formula, and that you understand how you can convert the fractional uncertainty into just uncertainty to add the unit, and then you can add it to your final answer.